Hello, dear students. Today we have Proposition 14 of Book 3. If straight lines in a circle be equal, they will be equal distant from the center. And if straight lines in a circle be equal distant from the center, they will be equal. Two propositions in one. Here we have two circles. Let it be the first case where we have straight lines equal to each other. Let this green line in this circle be equal to the red line, say. Thus it is required to show that these two lines are equally distant from the center. A little C there, remind us that that's the center, this right here. Okay? Let's drop from the center lines perpendicular to these lines. We know we can do that. Given a point down on a line, to drop a line perpendicular to a line. Okay? So now these are at right angles because we dropped these lines perpendicular. And we know that if in a circle, a line go through the center, cutting another line at right angle, it also bisects it. So this big line is bisected at this point, this big green line. Likewise here, this red line is bisected at the point of intersection of where the perpendicular falls. Good. Let's connect from the center these 2 points. Okay? So center falling on the circumference. Therefore, these are equal to each other, these two lines. The radii of the same circle. Okay? Now, if these are equal and these are halves of the whole, because this has been bisected and this has been bisected, halves of equals are equal. So this line right here, solid green line, is equal to the solid red line. Okay? Now look at these two triangles. They're both right angle triangles. Here's the right angle in this triangle, and here's the right angle in this triangle. Okay? So we know that in right angle triangles, the square on the hypotenuse is equal to the squares on the sides. And the square then on this hypotenuse is equal to the squares on the sides. But because these two things are equal, the squares on them are equal. So the square on this is equal to the square on this. But the square on this, because this is a right angle triangle, this is the hypotenuse, is equal to the square on this. So the square on this being equal to the square on this, and this being equal to the square on this and the square on this, the square on this is equal to the square on this and the square on this. See how that is used as middle term? Okay? But look, the square on this is also equal to the square on this and the square on this. So here you have this as a middle term, the square on this, that is. The square on this is equal to the square on this and the square on this, but it's also equal to the square on this and the square on this. So it brings the extremes together. The conclusion is that the square on this and the square on this are equal to the square on this and the square on this. But this is equal to this, and the square on this, therefore, is equal to the square on this. So let's take equals from equals, and therefore the remainders are equal. Okay, remember, the square on this and the square on this were proven equal to the square on this and the square on this. The square on this and the square on this are equal, so you take equals from equals, the remainders are equal. Therefore, the square on this and the square on this are equal. Therefore, the line is equal to the line. If the squares are equal, the lines are equal. So this is equal to this. Okay? But we know that from the definition, I don't remember, 5 or something of book 3, that in a circle, if lines be dropped at right angles to other lines, and those two lines are equal, those two lines are equally distant from the center. Again, in a circle, we have by definition, in a circle, lines are said to be equally distant from the center when the perpendiculars falling on them are equal. Okay? So here we have the circle with lines and perpendiculars falling on them being equal. Those lines are said to be equally distant from the center. That's what you mean by equally distant. Here you have a line, here's a center, and here's a line not equally distant. So therefore the perpendiculars falling on them, the one further away is going to have the longer perpendicular falling on it. If those two perpendiculars are equal, those lines are said to be equally distant from the center. That's by definition. We can talk about that one day. You have to see that immediately with your intellect. Okay, so since these things are equal, and they're both falling on these lines perpendicular, these lines are said to be equally distant from the center. Therefore, we've shown that if the lines in a circle, if lines are equal, they are equally distant from the center. Now let's have a different case here in our other center. And let's have lines which are given to be equally distant from the center. Okay, let's say, let's do it this way here, just make it a little bit different. Let's say, or let's have it be given now, that these two lines are equally distant from the center. Okay, thus it is required to show that these two lines are also equal to each other. Okay, we're going to have the same setup. We're going to drop lines perpendicularly, drop perpendicular lines. Okay. Oops, we're going to do this color now. And then we're going to connect from the center the points on the circumference. Okay? Let's see, make sure we get all our givens here now. These dropped perpendicularly. Great. And because these two red lines are radii of the same circle coming from the center, they're equal to each other. Let's see, these things are equally distant. And because these are equally distant and we dropped lines from the center perpendicular to them, by definition, these two lines are equal to each other. That's what you mean in the definition. Lines are said to be equally distant from the center when straight lines, perpendicular lines falling upon them are equal. So these are equally distant from the center, therefore the perpendiculars falling upon them are going to be equal. Okay? So here you have two triangles, two right-angled triangles, okay? And here you have two lines that are equal, therefore the squares on them are equal. But this is also the hypotenuse of this right-angled triangle, therefore the square on this is equal to the square on this and the square on this. Likewise here, the square on this being the hypotenuse of this right-angled triangle is equal to the square on this and the square on this. Okay, so these are equal, the squares on them are equal, and the square on this is equal to both this, square on this, and the square on this, and also the square on this. So the square on this is equal to the square on this and the square on this. So the square on this is equal to the square on this and the square on this as well, because it's a right-angled triangle. Therefore, acting as a middle term, the extremes are equal. The square on this and the square on this are equal to the square on this and the square on this. But the square on this and the square on this are equal because the lines are equal. So let's take away equals from equals, and the remainders are equal. The square on this is equal to the square on this. Okay? So this little green line right here, to distinguish it, let's make sure we're only talking about this part of it. Okay, these parts are equal. But we also know that this is half of this, because here you have a line coming from the center falling upon this line perpendicularly. We've proven that if that happens, it also bisects the line. So this has been bisected. This is half of this, or this is double this. Likewise over here, this is double this. But doubles of equal things are also equal. So this is equal to this, and this is double this, and this is double this. So doubles of equals are equal. This is equal to this. So therefore we have shown that if in a circle lines be equally distant from the center, they will also be equal to each other. Therefore we have shown both situations, both cases in proposition 14. If in a circle, lines in a circle be equally distant from the center, they will also be equal to each other. And if those lines be equal to each other, they will also be equally distant from the center. God erat demonstrandum. Bye bye.